Hi everyone, welcome to the video series on vectorization and embedding in natural language processing. In the previous video, we talked about bag of words and count vectorizer. In this video, I'll be explaining the concept or the limitations in the count vectorizer and how those limitations are addressed in TF-IDF vectorizer. And also, I'm going to show you the same text classification example now with TF-IDF vectorizer. Okay, so the TF-IDF vectorizer is the first step towards better semantic understanding in the text data. Let's see how it provides better semantic understanding. So let's recall some of the challenges or problems in the count vectorizer. In the count vectorizer, we stress on high count or frequency of the words in the input document. While the high count can be useful and informative, but at the same time, it can also pose some ambiguities and problems. Very high count can also dominate the representation and at times can introduce noise as well. Typically, the words that appear frequently, they are mostly stop words like the, and, is. This kind of stop words with a high count really does not help machine learning models discriminate the samples. So what happens is these common words start to dominate the vector representation, and that leads to poor model generalization. So this lack of discrimination is one big issue with count vectors. So this typically happens when the word appears many times in a single document, and that tends to dominate the representation. This can be problematic because a high count of a specific word need not be useful or may not mean or may not carry the intuition of importance or relevance. So to discriminate between the documents, high count may not be useful. So we'll see how TF-IDF handles that. As I mentioned, the high count can introduce noise in the vector representation, and the noise in the NLP models can also introduce, the fluctuations in the model predictions. Count vectorization, like BOW, discards the information about the word order and word semantic. This is also the problem with TF-IDF. TF-IDF does not address this particular problem, but the loss of context because of the no preservation of the word order affects both count and TF-IDF vectors. So, what are the techniques that we can apply to handle the high count or the problems associated with the high count? We can go with the term frequency and inverse document frequency method, or we can try some different or exhaustive text preprocessing techniques to address this problem. Address this problem. So let's understand each of the term here, the term frequency and the inverse document frequency. The term frequency is simply how many times the token is appearing in a particular document or particular input document. And the inverse document frequency is based on how common is the word across the document. Let's look at the formula for the term frequency. It measures how frequently a term appears in a particular document, how often the word occurs in a document. So term frequency is simply the frequency that we saw in count vector and is denoted by the number of times the word appears in the document divided by the number of tokens in that particular document. So let's talk about the document one, and it has 200 words. Out of that, let's say one word, cat, and that appears 5 times. So the term frequency of cat is going to be 5 over 200. That's what it means. It is similar to 5 that we saw in count vector. So what is inverse document frequency? This is the most important part of this computation, inverse document frequency. This measures the significance of the token or the word across the collection of document. That means how rare is that particular word when you look at all of the document, or how popular or how common it is across all of the document. Let's see mathematically what is the meaning behind that. So this simply quantifies how common or rare a word is across the corpus. The formula is quite easy. So let's see here. Let's say you have total number of documents is n divided by, so this numerator is capital N and this denominator is small n. That means the number of documents containing the term, let's say the term is cat, and the number of times the cat appears in the document divided by, let's say you have 1 million, um, 1 million total number of documents, and out of that 1000 of them have the word cat in it. So this is the meaning of the document frequency inverse. Why inverse? Because we are putting the total number of documents in the numerator and the number of documents which has the word cat in it in the denominator. And then we apply a log. Why do we apply a log? Just for scaling purposes. And we will see with an example how applying log really helps. So the TF-IDF formula is the term frequency that you computed multiplied by inverse of the document frequency of that particular term. Let's take an example here. We have the document 1, 2, 3, and these are the sentences here. We'll focus on one term called dog here in the first document. The term frequency of dog in the document 1 is 1 because the word dog appears only one time. Inverse document frequency means how rare or how common is the word dog across the three documents. Total number of documents is 3 divided by 2 is the total number of documents where the word dog is appearing. Here is one, here's another instance. So this is log of 3 by 2, and this is going to give you 0.176. This is the IDF of the word dog. Now TF-IDF of the word dog in the document 1 is going to be the term frequency, which is 1 multiplied by 0.176. Now you notice here the intuition behind this is out of 3 documents, 2 are containing the word dog. That means it is pretty common relatively, and hence the term frequency for dog, which was 1, now the TF-IDF, because of the formula, this 1 is reduced to 1.176. So this is kind of, rationalizing the weight of the token because it is very common. If it is very common, bring it down. If it is not very common, then increase the weight. We'll see how that really happens. So let's take an example, of a token, and the token is just a second. Let me go back here. Yeah, let's say the token is, the word cat, for example. And this word cat, the term frequency is 10. And the number of document that we are talking about is, let's say, 100,000. And out of 100,000, we have 100 documents the contain the word cat in it. So my TF-IDF score is going to be 3 multiplied by log of n divided by n, and that's going to be 3 multiplied by 100,000 divided by 100. So this is going to be 3 multiplied by log of 10 to the power 4, and hence this is going to be 3 multiplied by 4, that's 12. So if you look at it relatively, out of 100,000 documents, only 100 documents contain the word cat. That is relatively um, uncommon or rare. Since it is rare, see the term frequency, which was originally 3, has become 11 or 12, sorry. So that means we have increased the weights here. Now imagine um, your small n is not 100, but rather it is, let's say, something like this, 10,000. Okay. So in this case, we'll be dividing by 10,000, and that will remain, that will come like log of 10. So the value would be 3 multiplied by log of 10, which is going to be 1. So your turn frequency here in this case is not increased. It's not increased because the word is present in many, many documents. So this is balancing of the weights because of the TF-IDF score. So the interpretation is higher the TF-IDF score, that indicates the term is both frequent and also it is rare. So when the word is rare across the document, the score will go up. That means we are going to pay attention to the words which are having high TF-IDF score when we analyze the text data for classification or clustering or understanding which columns or which words contribute to the predictions. Now, the use cases for TF-IDF pretty much the same, where we use count vectorizer, but because of its better performance, TF-IDF is used in most of the traditional NLP application, for example, information retrieval, document summarization, keyword extraction, is also used in classification. In fact, I'm going to be showing you an example of text classification using IMDb dataset, and I'll be using TF-IDF vector there. It can also be used for recommendation system. Let's say you have a couple of PDF books or articles or a movie or a couple of input records which are textual in nature. You can do TF-IDF vectors and then compare the cosine similarity, and then looking at the angle or the similarity score or dissimilarity score, you can decide whether to recommend or not. So the advantages of TF-IDF, it is actually a good mechanism which balances the importance of the word based on the frequency and also on the fact that how rare or how common or how uncommon is the word across the corpus. So more common the word, it will weigh down the score, and rarer the word, it will increase the weights. So this is discriminating against the most frequent item. This is what we want. I mean, that was the problem with the count vectorizer. But there are some limitations. Most of the limitations are going to be the same that we saw in count vector method. This one, TF-IDF, also does not preserve the word order. So in terms of semantic, although this is the first step towards a better semantic understanding, still it suffers from the problem of loss of order of the tokens or the word. And hence the contextual understanding is also quite limited in case of TF-IDF. Fixed vocabulary size is exactly the same problem that we saw in the count vector. Here also we have a problem of fixed vocabulary size based on the length of the corpus. The TF-IDF will count or come up with the bag of word, which is basically the unique set of tokens, and that describes the size of the vocabulary. Equal weighting of the terms. Now, this is um, because of the balancing, you have some advantage, but as far as the algorithm goes, it does not differentiate between the type of words like, you know, adjectives or nouns and pronouns anyway different. So sparse representation is also the similar problem here as we had in the count vectorizer method. Lastly, I'm going to show you the similar text classification example on IMDb dataset, but this time it's going to be using TF-IDF, and probably we'll see a slight improvement because we will be using TF-IDF vector. Yeah, so back to this example, movie sentiment analysis. Here I will be using IMDb dataset, and we will convert the data into a TF-IDF vector. We'll apply the same machine learning model, multinomial Nye-based, and then we will do some evaluation based on the TF-IDF score. So data set is the same. I'm going to attach the data set and the code in the description below. So reading this is the data, and as in the count vector method, here also we're going to focus on the on this particular column, the cleaned text. And after that, we'll do a train test split for evaluation. So we're just going to focus on the clean text. And this time, the TF-IDF vectorizer. This is the vectorizer library, part of the feature extraction module. Set up your vectorizer, train the vectorizer, and also transform the training samples. So this is going to convert your training data, which is basically the clean text, into the into a vector format, and I'm calling that is as train matrix. Exactly the same thing on the test data, but this time no fitting, just only convert the test data into the format of a vector. Train the machine learning model, multinomial Nye-based, as I mentioned earlier. These models do very well with the discrete type of data, and here we're talking about frequencies and count and so on and so forth. So multinomial is a very good choice to set up the model, train the model, and predict. Let's do some evaluation, accuracy score, and so on and so forth. Notice we have a little improvement compared to the count method. Let's go back to the count method. And here we had 0.84. In the TF-IDF method, we have 0.86, which is significant improvement without doing any additional pre-processing. We just changed the vectorization method. And because of this, you have a lower false positive. So let's see how many false positive we had in the count method. We had 600 of them. With the TF-IDF, we have a lower, instances of false positive, which is pretty good. As usual, you should always, analyze for the false positive why the model is predicting a negative review as positive one. And the AUC score also has improved. Let's check for in the count method how much was the AUC. It was 0.91, and in the TF-IDF we have slightly improved 0.93. That's a welcome improvement. And ROC AUC is also slightly much better here. Let's evaluate the most frequent, top top terms in the by the TF-IDF score. And here you can see here again the same problem. The word like the and they have high TF-IDF score, and that gives you the indication that we need to go for slightly more stringent stop word removal, or more pre-processing, and so on and so forth. Conclusion is a slightly improved result, but still many of the top words are common in the positive and negative comments. That is not desirable. And many of the top words look like stop words, so consideration needs to be given to remove them or keep them. Need for more pre-processing and probably a better vectorizer, like a dense representation, would be a good choice. I hope this demo was useful and informative. Yeah, so that was the coverage on TF-IDF concepts, intuitions, and a little bit of mathematical explanation, along with the text classification example on IMDb dataset. We saw a little bit of improvement on by using TF-IDF. That's pretty much it. In the next video, we will talk about um, how TF-IDF or count vector methods are not really suitable for online machine learning model. And we will again look at the IMDb text classification and example, and we'll look at those exact limitations. See you in the next lecture. Thank you all.